Hi. In this video, we are going to look at a few advanced problems on combinatorics. And I'm going to show you a few problem solving techniques that are useful in Olympiads. So examples of these are you have to think of invariants, you have to think of parity, basically examples like that, where it's sort of a combinatorial um, game and where you have multiple steps and you have to arrive at a problem by thinking about the consequences of each operation. So let's get into the problems and we'll see what we can learn from these. So the first question is this: seven vertices of a cube are marked with are marked with zero, and one vertex is marked with 1. Now we have to do the following operation. So operation is specified as follows. So add 1 to the numbers on the end points or vertices of an edge. So the operation is this: you take any vertex and you add 1 to you take any edge of the cube and you add 1 to both the vertices at the ends of that edge, right? We can repeat the operation many times. We can repeat the operation as many times as needed. And the question that is being asked is basically, can the 8 numbers be equal? Can the 8 numbers ever be equal? After doing a finite number of operations, can the 8 numbers be equal? And the second question is, can the 8 numbers all become multiples of 3? Multiples of 3. So basically the 7 vertices are marked, 7 are with 0 and one of them is 1. And you can perform an operation where you increase the number marked on the 2 vertices connecting an edge. So you can increase it by 1 each. And you can repeat this operation any number of times. The question is, can the 8 numbers ever be equal? And can the 8 numbers all be multiples of 3? So think about it. So we'll look at the first part of the question here. So to think of the first part of the question, think of the sum S of all the numbers. S is the sum of all the numbers. All the numbers on the vertices. So you can see that S initial is equal to 1, right? And in each operation, you are going to increase the value of S by 2. Increases the value of S by 2, right? So what that means is, since the starting point is an odd number, S will always be an odd number, right? S will always be odd. So if the 8 numbers are all equal, if 8 numbers are all equal, then S should become even, right? Then S becomes even, because then S is divisible by 8. So we know that S will always be odd, and in this situation S is becoming even, which is a contradiction. Basically that is impossible now. So we can say that the answer for this first part is no. And the simple method that we used was you used the parity of the sum of all the numbers on the vertices of the cube. which was odd, and after every operation it stayed odd. It cannot become even. Therefore, the first part is not possible, right? Okay, now think about how you would figure out the second part. Can all the 8 numbers become multiples of 3, right? Okay, so what we can do here for the second part is we select 4 vertices from the cube so that any two of them are not the endpoints of an edge, are not the two endpoints of an edge, of an edge, right? So we call these 4 vertices, we find the sum of the numbers here, find the sum of numbers on these 4 vertices, and we say that that is equal to A, right? And we say B is the sum of the numbers on the remaining 4 vertices, sum of the numbers on the remaining 4 vertices. So we have selected the 4 vertices here, which are not, any two of them are not the vertices of a single edge. And we have summed up the numbers on those vertices. We call it A. And we call B as the sum of the numbers on the remaining 4 vertices. Now what I will show you is the concept of an invariant. And what we can see is that the quantity T is equal to A minus B is always invariant or always constant. Why is this always constant? You can repeat the operation any number of times. The value of A minus B will always be constant. In the beginning, T starts off with a value of plus or minus 1. Why? Because you can pick the 4 vertices in A, all of them could be 0, 0, 0, 0, and then the remaining vertices here will be 0, 0, 0, 1. In that case, the value of T will be minus 1. Or you can pick the one vertex in A set and the other vertices are 0. So that case, it would be plus 1. Now, whenever you do an operation, what you will realize is if these are the vertices, every time you increase the value of an edge by plus 1 and plus 1, this plus 1 goes to a number in the A set and this plus 1 goes to a number in the B set, right? So therefore, both the sums of the A set and the B set are increasing by the same value plus 1, and therefore the value T, which is A minus B, is always remaining the same, right? Now think about it. If all the 8 numbers are divisible by 3, then A set will be divisible by 3 and B set will be divisible by 3, and therefore T, which is A minus B, is also divisible by 3, right? That is true. T will also become divisible by 3. But what did we find out here? T was equal to plus 1 minus 1 and it does not change. So it can never be divisible by 3. So therefore, this is a contradiction. And we have proved that the second case where the 8 numbers are all multiples of 3 can never actually happen, right? So that is the way in which we have used invariants here in this problem. It was a very simple question, but you have to learn the technique of choosing an invariant and solving it accordingly, right? So that is an example for that technique. Now, the next question is this one. N students take a math exam. The exam has M questions. And there are the following statistics were observed. Following statistics were observed. Here, alpha is a real number between 0 to 1. Second, at least alpha times m problems are difficult problems. Are difficult problems. And what is the definition of a difficult problem? A difficult problem, a difficult problem is that which is one where at least alpha times n students have not solved it. Have not solved it. So what is a difficult problem? A difficult problem is one where alpha times n, some fraction of students have not solved it. And the statistic that was observed was that at least alpha times m problems are difficult problems. And the third statement was at least alpha times n students pass the exam. And how do you pass an exam? A student passes if they solve at least alpha times m problems. So this is the statement of the problem. There are n students, m questions, and alpha is a real number. At least alpha m problems are difficult problems. What is a difficult problem? Is one where alpha n students at least have not solved it. And so the third thing that was mentioned was alpha n students pass the exam. And how do you pass the exam? If at least you have solved more than or equal to alpha m problems, you have passed the exam, right? The question is asking us, try to determine if the above situation is possible, if the above situation is possible for alpha is equal to 2 by 3, alpha is equal to 3 by 4 in these two cases. Check whether this situation is possible for alpha is equal to 2 by 3 or alpha is equal to 3 by 4. So we'll try it here. The first thing that we'll say is we'll check for alpha is equal to 2 by 3. Okay. Now, one way to prove such questions is to construct a counter example. So what I will try to do is I'll try to set up a situation where alpha is equal to 2 by 3 is possible. Okay. So let's suppose there are n is equal to 3 students and there are m is equal to 3 questions. And the students are called S1, S2, S3, and the problems are called P1, P2, P3, right? And let's assume that S1 has solved P1 and P2, P1 and P2, S2 solved P1, and S3 solved P1, right? If you think of this case, now alpha is 2 by 3. So passing mark is how much? Passing mark is 2 by 3 into 3. So you have to solve 2 questions to pass, right? And we can see that only S1 passes. Uh, 1 second. Uh, S2 solved P1, then he won't pass, right? So I'm trying to think of a way to make sure that at least alpha n students pass. So alpha n students is 2 students should pass. And passing situation is alpha times m. Okay, two questions have to be solved. So we can set it up as P1 and P3, right? P1 and P3 has been solved by this. So here we can say that only S1 and S2 have passed, which is alpha times 3 or alpha n, right? So at least alpha n students have passed. And which ones are the difficult problems? P1 is an easy problem. P2 has been solved by only P2 was solved only by S1 and P3 was solved only by S2, right? So actually P2 and P3 are difficult problems because P2 was not solved by S2 and S3, not solved. And similarly, P3 was not solved by S1 and S3, right? So why is it difficult? Because alpha times m students, alpha times n students have not solved it, or 2 students have not solved these problems, right? So basically we are getting 2 problems are difficult, 1 problem is easy. P2, P3 are difficult and P1 is easy. And similarly, 2 people have passed S1 and S2 and 1 person has failed S3. So this basically satisfies the condition of the first part of the problem. For alpha is equal to 2 by 3, we have set up a situation where all the conditions of the problems is done, right? At least 2 problems are difficult, at least 2 students have passed, right? So that is an example that shows us that it is possible for alpha is equal to 2 by 3. However, let's now look at about the case where alpha is equal to 3 by 4, right? Now we'll do it in a more general way. We'll not try to construct an example because it will become very confusing. So what we'll say is let R be the number of difficult problems, and P be the number of students who passed, be the number of students who pass, right? What we will do is we will list out all the problems like this: P1, P2, PR, and then further till PM. There are M problems. These are the difficult ones. And we list out the students also like this: S1, S2, ST, and then till SN. There are N students, and these are the ones who pass, right? And what we'll do now is construct a table. So we'll make a table like this. How do we make the table? We label the problems here: P1, P2, PR here, and finally PM here, and S1, S2, ST here, and finally SN here. And this is a array, M cross N array, right? Or a matrix, whatever you want to call it. And what we will, the rule for filling up this matrix is if SI solved PJ, student I has solved problem J, we put a 1, otherwise we put 0, right? Otherwise we put a 0. So what we can say is every problem and every student we can mark whether he has solved it or not by 1, 0, 0, and so on, right? So what we will do here is the table will be filled. Table is filled with m times n integers. The size of the table is m times n, right? Many of them will be 0, some of them will be 1. But there are total of mn integers in the table, right? And now what we will do is we'll try to estimate the number of integers in a slightly different way, okay? So we will do it in this way. We'll say I will just create some space here. Okay. So we'll say because the students who passed have solved at least alpha m problems, have solved at least alpha m problems. So there are at least alpha m ones in the first t rows. First t rows. Why? Because the first t rows are the students who passed, and for passing, you need to solve at least alpha m problems. So every student who passed has at least alpha m or more ones, right? In his row. So there are total number of alpha m ones in every row for the first t rows for all the students who passed. So the number of ones in the table is greater than equal to t times alpha m, right? Obviously, these are the number of ones that appear in this section of the table. For the first t rows, at least this many ones. Now we know that t, in the problem it has been said that the number of students who passed is at least greater than equal to alpha n. Excuse me. The number of students who pass t is greater than equal to alpha n. So we have this is greater than equal to alpha n times alpha m, right? Which is basically alpha square mn, right? Great. Similarly, we know also there are at least alpha n students, at least alpha n students who have not solved every problem, who have not solved every problem. So now we are going to count the number of hard problems, right? So in the first R columns, there are zeros, right? At least alpha n zeros. Why are these problems hard problems? Because at least alpha n students are not able to solve these problems, right? So you have to have zeros, at least alpha n zero in every column for the first R columns. So the number of zeros in a similar way is greater than equal to R times alpha n, and R, which is the number of difficult problems, is greater than equal to alpha m. So that will be equal to alpha m times alpha n, which is also alpha square mn, right? So there are at least this many zeros and there are at least this many ones. So the total number of integers, number of zeros plus number of ones in this table is greater than equal to 2 alpha square mn, right? But we know from our initial discussion that the whole table has to be filled with zeros and ones. So actually we know the number of zeros and number of ones because the whole table is only filled with zeros and ones and there are mn spots. So we know mn is greater than equal to 2 alpha square mn. The left hand side has to be mn, and from here we are getting an inequality. So we have this situation happening, right? Now this means that when you divide, you get 1 is greater than 2 alpha square. Therefore, alpha square is less than equal to half. And now we know that there is an upper bound on alpha. Alpha should be less than equal to 1 by root 2, right? Therefore, we realize that for 3 by 4, alpha square is equal to 9 by 16 and alpha square is greater than half. So therefore, alpha is equal to 3 by 4 is not possible in this situation. I hope you are understanding the logic. We are counting the number of integers in the table. The total number must be mn, and we have found an inequality on the number of ones and the number of zeros. Once we establish the inequality, we are getting a condition on alpha square, right? That helps us prove that the second case is impossible. Alpha is equal to 3 by 4. Whereas the first case was done. Alpha is equal to 2 by 3 was established by taking a simple example. We just set up the situation ourselves. Okay, let's look at the next problem. This is question number 3. At a party, each participant has at most 3 acquaintances. At most 3 acquaintances. Prove that the participants can be classified. The participants can be classified into two groups. So that each person has at least one acquaintance in his or her group. This is the question, very simply stated. We are saying each participant has at most 3 acquaintances, and then we can always classify the participants into 2 groups such that every person has at least one acquaintance in his group, right? So what we'll say here is, first step is randomly divide the participants into 2 groups. Participants into group 1 and group 2, right? Now we say let S be the sum of the number of acquaintances of every participant in a single group. So basically for group 1, we will say not in a single group, actually for the whole group. So we will say let S be the sum of the number of acquaintances of every participant in his or her own group. So what is the meaning of this? So suppose there was group 1 had 3 people, group 2 had 2 people, right? Let's say in group 1, these 2 people knew each other, A, B and A, C, and group 2, D and E knew each other, right? So this is the set of acquaintances. When you are acquainted, both the people know each other, right? So you can say, what will be S for this situation? We will say A knows how many people in his group. A knows 2 people, right? So for A, the number is 2. B knows A, so B, the number is 1. C knows A, C, the number is 1. And in this group, D knows 1 person, so D number is 1, and E knows 1 person, right? So this is the sum of the number of acquaintances of every participant in his or her own group. Here we are not counting, maybe perhaps A knows E, or perhaps D knows C and B knows D, right? Those are not taken into account, right? For group 1, we will count each person knowing how many people in the same group. That will be the number assigned to each person. Similarly, for A it is 2, B is 1, C is 1. Similarly, D in his own group, he knows 1 person, so his number is 1, and E also is 1. So that is basically the meaning of the S term. S is the sum of the number of acquaintances of every participant in his or her own group, right? And we do it for the entire set of all the participants, right? Okay. So now we say, suppose there is a person A, there is a person A in group 1 who has at least 2 acquaintances in his group. So the total number of acquaintances is either 2 or 3. At most 3 acquaintances are there. So maybe there is a person in group 1 who has at least 2 acquaintances. So it could be 2 or it could be 3. So what we do then we transfer A to group 2. If there is a person like this in group 1 who has at least 2 acquaintances, we transfer A to group 2. Now what does this affect? How does this affect the value of S? Think about it. The value of S will change due to this transfer, right? So suppose A knew 2 other people in his group, then those 2 people have lost an acquaintance when A went to the other group, right? So at least 2 people lost an acquaintance, right? Now it is possible that A knew someone in the other group, and since now he is gone to the other group, that person will gain an acquaintance, right? So, but the point is that since there are at most 3 acquaintances, there are 2 people in group 1 who lost an acquaintance, but at most 1 person in group 2 who gained an acquaintance. Group 2 who gained an acquaintance, right? And apart from that, you can think of A's number itself. A had 2 acquaintances in group 2, but when he transferred to group 1, A had 2 acquaintances in group 1, but when he transferred to group 2, he lost an acquaintance, right? So his number has reduced by -1, right? So basically, overall, you can see that S is decreasing. Definitely, the value of S will decrease if you transfer such a person A to the other group, right? Okay. Now, since S is strictly decreasing and S is going to be a natural number, what this means is we know that the sequence of natural numbers can only sequence of strictly decreasing natural numbers. Strictly decreasing natural numbers can only have a finite number of terms, can only have a finite number of terms. So you cannot keep reducing S forever, right? So what will happen is after some time, it will be impossible to reduce S further. Impossible to reduce further because the sequence of natural numbers which are decreasing has a termination point. So what this means is there will be no further person like A in all of the groups after some point, right? So that means eventually you will come to a situation where there will be no person like A who has greater than equal to 2 acquaintances in a certain group, in a group 1, right? Such people will all disappear. And eventually you will be able to say that in the whole grouping, there are always, every person has at least 1 acquaintance in his group, but you cannot say that every person has at least 2 acquaintances, right? So we are saying that the situation is possible. So the participants can be classified into 2 groups so that each person has at least 1 acquaintance in his or her group. So the desired grouping is reachable. If you are confused about it, think about the original example. Let's say there are 6 people, A, B, C, D, E, F. And let's say the acquaintances are like this. A is acquainted with B, A is acquainted with C, A is acquainted with D, then B is acquainted with E, B is acquainted with C, and D is acquainted with F. And let's say we put E is acquainted with F also. These are the acquaintances. We have randomly divided into groups. So now think of the S value initially. What is the S value? For A and B are linked, A and C are linked, B and C are also linked. And for D and F are linked, E and F are linked, and D and E are not linked. This is the situation initially, right? So the S value initially is what? For A, he is linked to B and C, so 2. For B, there is 1. For C, there is 1. And for D, there is 1 because D is linked to F. And E, there is 1, right? So the value of S is 6 initially. Now we can see here that there is a person here, A, who is linked to 2 people in his group, B and C. And A is also linked to D, but D was in the other group, right? So we do the transformation, we shift A to the second group. So what do we do now? We remove A from here and we put A in the second group here, right? So as a result of this, what has happened? As a result of this, let's think about what has happened. Here B and C are still linked. Now A and D are linked, and D and E were not linked. D and F were linked, and E and F were linked, right? Now think of the value of S here. The S value now is for B it is 1, for C it is 1, for A it is 1, for D it is 1, for E it is 1, correct, and for F is also 1, right. So what has happened is B is 1, C is 1, A is 1, D is 1. No, actually what happened is D became 2, right? D is linked to 2 people now, correct. A, B, and C is 1, D is 2, right. And E and F is 1. And earlier, I think we have made a mistake in counting. We had A was here, and A was linked to 2, B and 1, C is 1. So 2 plus 1 plus 1 was there. And D, E, F, we wrote D is 1, E was 1, F was 1, correct. So earlier here it was S is 6, and now we are getting S is 7. So basically, we have not done the complete transformation because we should have transferred D to this side also. So the step that we wanted to do was replace all the people in different groups, right? So we shifted A to this side, we should have automatically shifted D also to the other group, right? So the point is, there are 2 people like that. If we shift D to this group now, what happens is the value of after shifting, it becomes now D is not linked to C, D is not linked to B, this is it. And A is linked to E. No, E is linked to F. And we have basically, that's it, right? Okay, so in this case now, what we have is B and C have 1 and 1, D has nothing, A has nothing, and E and F have 1 and 1. So now we are getting S is equal to 4. So basically the idea was, one step, the value of S increased momentarily, but when you do the next step, when D was sent from here to here, the value of S decreased to 4. And now there are no, we can say that there is no person here who is such that it has greater than equal to 2 acquaintances, right? Correct. So basically the idea is we are reducing the number of S, and by the principle of infinite descent, we are able to say that always the value of S keeps decreasing, and therefore we are never going to come to a situation where it will forever continue. Eventually, we are going to come to a situation where the grouping is such that there are at least one acquaintances in each group, right? Okay, let's look at the next problem. Question number 4. Let S be a set of 2n points in a plane where any 3 points are not collinear. Now color n points red and n points blue. Prove that n straight line segments that are pairwise disjoint or non-intersecting can be found such that the two endpoints of the line segment, the two endpoints of each line segment have different colors. There are basically two endpoints in a plane where any 3 points are non-collinear. We color half of the points as red and half of the points as blue. And we have to show that it is always possible to find n line segments using these two endpoints such that they are pairwise disjoint, and these line segments are non-intersecting with each other, and they have different colors on their endpoint. Okay. So what we will say, because there are only n pairs of points, there are finitely many ways to match red with blue points. There are a finite number of ways to match red and blue points. Right? That is correct. Now, every time we match red and blue points, we can label the points and we'll get a different arrangements of points where we are matching or we are pairing up red and blue points, right? So we are saying for each pairing method, let's call it a pairing method pi. So this is a way to pair n red points with n blue points. Obviously the points are labeled, so there are finite number of ways to pair them, right? So for example, you have red 1, red 2, and blue 1, blue 2. We can pair it like this: R1, B1, R2, B2, or we could do a pairing R1, B2 and R2, B1. So these are only two pairings possible, right? This is a possible pairing, pi 1 and pi 2, right? For 4 points. So what we are saying is, for 2n points also, there will be finite number of such pairings possible of red and blue together, right? So for each pairing method, what we will say is, consider consider the sum S of pi of the length of the n line segments. N line segments. So obviously, since there are two endpoints and we are pairing 2 points together, so there are n different line segments that are there. For example, here there were 4 points and there were 2 line segments, right, in each pairing. In pairing 1, the line segments are R1, B1 and R2, B2. In pairing 2, the line segments are R1, B2 and R2, B1. So consider S pi is the sum of the lengths of the n line segments. So S pi 1 would be R1, B1 plus R2, B2. S pi 2 would be R1, B2 and plus R2, B1. So what we are saying is this sum of the n different line segments, there must be a certain pairing. There must be a certain pairing pi, which minimizes S pi. Why? Because there are finite number of pairing methods. So finite number of pi is possible. In any finite set, there always is a minimum value, right? There are finite number of S pi's possible. So therefore, in any finite set of real numbers, there will be a minima. So there will be certain pairing pi which minimizes S pi, right? Great. So we are thinking about, suppose we are assuming that this minimum pairing has, suppose there is a line segment, RB and another line segment, R dash B dash in pi, such that RB and R dash B dash intersect. So what are we saying? Be very careful here. We are saying that there is a pi such that it minimizes this S of pi. So the sum of the lengths of the line segments in this pairing is minimum. And we are now assume that one of the pairs RB and R dash B dash here, these are two different line segments in pi intersect. Assume that they intersect, right? So now we will show that we can replace RB and R dash B dash with RB dash and R dash B. So suppose this is my R and B and this is my R dash B dash, and suppose they were intersecting like this, right? So what we are saying is, if you have RB and R dash B dash in my minimum pairing, I could have replaced it with these two lines now, RB dash and R dash B. Now, because of triangle inequality, let's call this M, we can say that R dash M plus MB is greater than R dash B, and we can say that RM plus MB dash is greater than RB dash. So when you add this, you get R dash M plus RM plus MB plus MB dash is greater than R dash B plus RB dash. Now, if you think about it, RM plus MB is equal to RB, and R dash M plus MB dash is equal to R dash B dash. So we are getting R dash RB plus R dash B dash is greater than R dash B plus RB dash, right? So what we are saying is, if we have a pairing pi such that there are two line segments that intersect, we could replace the line segments RB and R dash B dash with these two line segments instead. Using the same 4 points, we have gotten two new line segments, but now the sum of this and this length is always lesser than the sum here. That means the new pairing pi star, which has these two line segments instead of these two line segments, will have S of pi star will be less than S of pi, right? But that is a contradiction to our initial assumption that there is a pairing pi such that it minimizes S pi, because now we have a new minimum, right? So that means something is wrong in our assumption here. The assumption that is wrong here, because we have arrived at a contradiction, the assumption that is wrong is this, that RB and R dash B dash can intersect, right? So otherwise we'll come at a contradiction and we are getting a new pairing with a lower minima, right? So that is wrong assumption. So therefore we have completed our proof that if you want to minimize the number of sum of the line segments length, then you will always be able to find a set of line segments which do not mutually intersect. So therefore we can say that n line segments in pi are pairwise disjoint. So we are able to find a set of n line segments in pi where all the red and blue points are grouped together such that all the line segments are mutually disjoint, pairwise disjoint. Why are we able to find it? Because always in any pairing, we will be able to minimize the sum of the length of the line segment. Because it's a finite number of pairings, so there is always a minima in that group. So we are using the extreme principle here, and we are using the fact that for any finite set of real numbers, there is always a minima, right? Because we have used that, that's why we are able to prove this. We look at one final problem. This is this one. Several people attend a party and some of them know each other and some of them know each other. It is known that one, if two people have equal number of acquaintances, then they don't have a common acquaintance. Then they don't have a common acquaintance. The second thing that is known is that there is a person in the party with at least 100 acquaintances. With at least 100 acquaintances. And we have to prove that there is someone with exactly 100 acquaintances. So again, the question is a little tricky. We are given information that some people attend a party, some of them know each other. If two people have equal number of acquaintances, then they don't have any common acquaintance. And there is a person with at least 100 acquaintances. So that person can have 100 or more than 100 acquaintances. We have to prove that there is someone with exactly 100 acquaintances. Okay. Fine. So again, we are going to use the extreme principle here. So let's see how we do it. So consider any person A with acquaintances B1, B2 till Bn. And here n is greater than or equal to 1, right? Now, because A is the common acquaintance of all of B1, B2 till Bn. Basically, we can say that B1 and B2 both know A. Therefore, from the first condition, they cannot have an equal number of acquaintances, right? The first condition of the problem said that if two people have equal number of acquaintance, then they cannot have a common acquaintance. Here, all of these people, B1, B2, Bn, have a common acquaintance A, so they cannot have equal number of acquaintances in total, right? So we say that the number of people known by B1, B2 till Bn are different from each other, are different from each other. Great. Now we'll make the assumption that let's say, let A be the person with the maximum number of acquaintances, with the maximum number of acquaintances. Obviously, there must be a person or persons whose number of acquaintances is maximum because it's a finite set of people who come, right? So A is the person with the maximum number of acquaintances. So therefore, the number n, A knows n people, and because A knows n people, we know that B1, B2, Bn, they are all less than equal to n, right? Because A knows n people and B1, B2, Bn have to be less than equal to n because A was the person with the maximum number of acquaintances. So these people cannot know more than n people, right? And also we know from the previous fact that B1, B2, Bn are all different from each other because they all have a common acquaintance. So there are n people, n numbers different from each other and less than equal to n. So obviously B1, B2, Bn is an arrangement of 1 to n, right? It must be a permutation of 1 to n because there are only n numbers in 1 to n and there are n different numbers here, right? Great. Now we know that A is the maximum, right? A is a person with the maximum number of acquaintances. And in the second part of the problem, it was said that there is one person with at least 100 acquaintances. So we know that A knows n people, so n must be greater than equal to 100. If n is greater than equal to 100, that means 100 appears in this sequence, right? In this sequence of numbers 1 to n, right? Because n is greater than equal to 100, 100 will appear in the sequence of numbers 1 to n, correct? Right. So that means that there is a person among the acquaintances of A who knows 100 people exactly, right? Why? Because we saw earlier that this was B1 to Bn is a set of n different numbers which is equal to a permutation of 1 to n. And 1 to n we have now realized because A is the person with maximum number of acquaintances, 1 to n goes from 1 to something above 100. So 100 is going to be present in that sequence. And if 100 is present in the sequence, there must be a person who knows exactly 100 people. It could be B53 or B48 or whatever, but there is a person who has 100 acquaintance, right? So again, we have used very cleverly the extreme principle. we have said that there is a person who is the maximum number of acquaintances, and using that and the conditions of the problem, we are able to solve it. So hopefully these 5 problems should give you a taste of the kind of questions that you might see in an Olympiad. You need to apply the principles of invariance, principles of parity, thinking of extreme cases, maxima, minima elements, and transformations, doing an operation on a set. Basically, it's a combination of all of these tricks that you will encounter in your questions. So hopefully you learn something from this, and I'll see you next time with the new section in the course, which is on number theory. So that's a good point to stop.